All right, let's dive straight into this explainer. We're going to explore the elegant mathematics and, honestly, the hidden reasoning behind uniform circular motion. We'll be starting right from the passenger seat of a turning car and taking it all the way to the very edge of Einstein's theory of relativity. Here is our roadmap for today. We've got 6 key areas: the acceleration illusion, the math of spinning, the center-seeking force, the centrifugal force myth, real-world circular motion, and finally, from apples to space-time.
Section 1, the acceleration illusion, driving in a curve.
So imagine you're in a car, right? And you're driving on a curve at a perfectly locked speed of 60 kilometers per hour. Now, I want you to ask yourself, how is it that you can physically feel a push or a lean? The number on your dashboard is glued to 60, yet your body absolutely knows you aren't driving in a straight line.
Well, this comes down to that classic physics distinction between speed and velocity. You see, speed is just the magnitude, right? But velocity is a vector. It's your speed combined with your direction. And because your direction is continuously changing on that curve, your velocity is changing too. And a change in velocity, that means you're technically accelerating the entire time, even if that speedometer never twitches. Crazy, right?
Which brings us to uniform circular motion. By definition, this is moving along a circular path at a constant speed, where only your direction changes continuously. Your speed remains perfectly fixed while you relentlessly redirect your path. That word uniform is really doing a lot of heavy lifting here. It means equal arc lengths and equal time intervals. Literally, only the direction alters.
Moving on to Section 2, the math of spinning, angular versus linear speed.
Okay, picture 2 horses side by side on a merry-go-round, completing one full revolution in the exact same amount of time. They share the exact same angular velocity. However, think about the outer horse. It has to cover a much larger circumference. This means it physically moves through space faster, having a higher linear speed, despite sweeping through the same angles at the exact same rate as that inner horse. And honestly, this is exactly why sitting on the outer edge of a spinning ride always feels so much wilder.
There's a really simple formula here, but it elegantly connects all these dots. Linear speed equals radius times angular velocity. It perfectly bridges how fast an entire object spins, its angular velocity, and how fast a specific point on that object actually travels through physical space. Put simply, the bigger your radius, the faster your linear speed.
Section 3, the center-seeking force, unpacking centripetal acceleration. Now, using pure geometric reasoning and some infinitesimally small time intervals, physicists realize something fascinating. This acceleration always points exactly toward the center of the circle. The formula is velocity squared divided by the radius. But notice that velocity is squared. What does that mean for us? It means if you simply double your speed going into a curve, your required acceleration doesn't just double, it quadruples. And that right there is exactly why race car drivers have to be unbelievably precise on tight corners so they don't spin out.
So let's follow the logic. If changing direction requires a center-pointing acceleration, and Newton's second law dictates that acceleration absolutely requires a physical force, well, then we're left with an absolute necessity. A real center-pointing force must exist for circular motion to even happen.
We call this centripetal force. But interestingly enough, it's not some brand new force of nature. It's really just a job title we apply to whatever ordinary force happens to be doing the work. For a ball swinging on a string, tension has the job. For a car turning a corner, it's the friction of the tires. For the moon orbiting the Earth, it's gravity doing the heavy lifting. Centripetal force is essentially just a label for whatever force keeps the object trapped on its curved path.
All right, Section 4, the centrifugal force myth. Let's talk about why your intuition is just plain wrong.
It is time to play Mythbuster with a sensation you have felt your entire life. When you take a sharp turn in a vehicle, you feel undeniably pushed outward, squished right up against the car door. But is there actually an outward force acting on you? Seriously, is centrifugal force a real physical thing pushing you away from the center?
Well, it turns out the answer is a resounding no. Your body's inertia just wants to travel in a straight line. What you actually feel isn't an outward push at all. It's the car door physically pushing you inward to force you along the curve. Centrifugal force is what physicists call a fictitious force. It only appears to exist because you're observing the world from inside a turning, accelerating frame of reference. If we were to watch you from outside the car, we'd literally just see a person trying to go straight and a giant car door pushing them into a circle.
Section 5, real-world circular motion, from washing machines to orbits.
Taking these concepts out of the abstract reveals the sheer brilliance of the mechanics of our everyday world. Think about it. Whether it's a steeply banked racetrack, relying on the normal force of the road instead of just friction, or maybe an amusement park rotor ride keeping you pinned to a wall after the floor drops away, or even your washing machine's spin cycle separating clothes from water, it is all the exact same physics. The clothes get pulled in a circle by the drum, but the water doesn't get that inward push, so straight line inertia flings it right out through the holes. It's beautiful.
And taking this all the way up to the skies, when engineers calculate orbital mechanics, they rely on gravity as the centripetal force. The math dictates that a low Earth orbit satellite must travel incredibly fast. We're talking around 7.8 kilometers per second just to avoid falling, because the gravitational pull is so much stronger closer to Earth. Meanwhile, a geostationary satellite sitting far out in space can travel much slower, around 3.07 kilometers per second, and perfectly match Earth rotation.
Now here is a little secret connection that physicists absolutely love. If you look at uniform circular motion entirely from a flat, side-profile view, literally just ignoring the depth completely, the mathematics identically matches a bouncing spring or a swinging pendulum. We call this simple harmonic motion. It reveals this deep, hidden unity in physics, where rotations and oscillations are secretly the exact same mathematics, just wearing different costumes.
And finally, Section 6, from apples to space-time. Let's look at the cosmic scale.
Zooming all the way out to the grand historical scale, humanity has slowly pieced together these universal rules over centuries. In the 17th century, Christian Huygens mathematically described circular forces while working on pendulum clocks. By 1687, Isaac Newton had a massive breakthrough. He realized that the exact same force dropping an apple from a tree is the force pulling the moon in its circular orbit, essentially unifying earthly and celestial mechanics forever. And then, in 1915, Albert Einstein came along and changed the game entirely with general relativity.
Today, these very same classical concepts are practically applied to guide protons at near light speed inside the Large Hadron Collider using superconducting magnets for centripetal force. But the real sense of awe, that comes under Einstein's general relativity. We now understand that orbiting objects aren't actually being pulled by some invisible force through empty space at all. They're just traveling in their natural straight lines through a fabric of space-time that has been geometrically warped by massive objects like stars and planets.
It really all connects. So, the very next time you feel pressed against the door of your car on a gentle curve, I want you to ask yourself, are you just going for a drive? Or are you experiencing the exact same breathtaking geometric mechanics that hold the entire cosmos together? Thanks for joining me on this explainer, and as always, stay curious.